Okay, let's get going. Good evening, everyone. Well, it's good evening for me. It's in Japan, hi gozaimasu. In Germany, guten Abend. In Israel, I don't know what you say at 1 a.m. in the morning.
Boker Tov.
So welcome to the third day of MLCAD, and it is officially the third day in Asia. So this morning's keynote will be jointly presented by Rajeev Jain and Pankaj Kukal from Qualcomm. Rajeev leads the machine learning R&D group for all aspects of SoC design, and he is a professor emeritus at UCLA and fellow of the IEEE. And he actually lives in Santa Monica, which is a hell of a commute. And if you don't know LA, that's through the entire LA basin if you actually commutes. And enjoys mountain running and biking there. Pankaj is the vice president for EDA emulation and validation at Qualcomm, and he's had a long career at Intel and other places. And he enjoys in San Diego water skiing and boogie boarding. I'll hand it off to the two of you. Thank you very much for doing this.
Okay, thank you very much. I will share my screen now and hope that all works well. Bear with me a minute. Okay, Paul, please let me know if you can see my screen.
Yes, I can.
Okay, and let me try to remove the overlays here. Okay, all right. So we'll get going here. And thank you for the introduction, Paul. And I want to thank my co-author, Pankaj, for inspiring many of the thoughts here. We're going to talk about data-driven CAD, which is kind of the emerging theme of this conference, MLCAD, and the traditional EDA or algorithm-driven CAD that we've known for 30 or 40 years. And the question is, are these two in competition with each other, or as we go into the future, are they going to complement each other? And that's the question we're going to try and answer today. So for starters, just to understand the bias we have in our talk from Qualcomm, the first important thing is that we are in a very high volume industry, which is smartphone and mobile chips. And so a lot of our thinking on design tools, design methodologies are impacted by the needs of high volume chip production, which means that even a small change in area, for example, has a huge multiplicative factor financially. And so that affects our thinking. The second thing is that although we are well known for our play in smartphones and mobile devices, but our chips are expanding into several areas now, including the edge cloud and the cloud itself. So there's a sort of horizontal heterogeneity of the kind of markets we're targeting with the chips. And obviously, to provide all the functionality in these markets, the chips themselves are heterogeneous platforms, with CPUs, GPUs, DSPs, AI processors, wireless systems, and so on. And so these three things, which is the high volume, the heterogeneity of our products, and the heterogeneity of the systems that go on the chip, these three things have a significant impact on how we think about design and design methodologies. And our goal is to deliver the best performance at the lowest power, since most of our chips do go into battery-powered products. So that's the fourth dimension that impacts the way we think about design. At a bird's eye view, there's, of course, investments in artificial intelligence and machine learning in many different areas in Qualcomm. The one that we'll focus on today is in AI-assisted design engineering. And the exploration in AI-assisted silicon design largely comes from two factors. One, as we near the end of Moore's law, Pankaj and his team and many of us are rethinking the design flows and methodologies as to how do we deal with this. The second, equally important factor influencing our thinking is how do we utilize the cutting edge design experience. We have incredibly smart designers who have year after year helped us to meet all the cutting edge requirements of all the customers with the chips. So there's a tremendous amount of design experience that we carry. and there's a tremendous amount of design data that embodies that experience. So how do we leverage that? How do we utilize that? So these are two key factors that are driving our thinking. Now, why rethink the methodologies? In many ways, we see a rapidly approaching cliff because the foundation on which we have built the chip industry, to our eyes at least, looks like it's under serious threat from many disruptions. So let's look at the foundation. And there are three things that we think we rest on or stand on. One is the notion of fabless chips, that we could actually do the design and have the chip fabricated somewhere else. And some of you might remember, Bartle Systems, which later becomes Cirrus Logic, was perhaps the first fabless chip, and was in fact founded on the basis of the very first version of standard cell or gate array concepts and layout tools that were developed at Cirrus that showed that you could actually, do these complex chips in a fairly automated way and ship off the masks to a foundry somewhere else and get the chips made. So that has been the mainstay of our industry. The second thing is that as the chips became complex, there was a whole design automation industry that grew up in the mid 80s and later to provide us with all kinds of tools to automate the design. And the third was the workstations. The early ones came from Sun and other companies that allowed designers very powerful graphics and computing to be able to run these design automation tools. Now, if you think about the key elements that actually are embodied in this foundation, on the fab side, it was clearly Moore's law. We had this luxury of getting enormous gains in power and performance for the same area or less area year after year, which we call the PPA scaling. And that allowed us to upgrade the chips and therefore the products and get people to go out and buy new things every year and fuel the growth of the industry. The second was the development of combinatorial optimization, starting with the early work of Alberto Sangiovanni and Richard Newton at Berkeley and many others, that led to algorithms that were fairly powerful at automating complex design implementation. And as computing needs grew with the complexity to run the design automation tools, we got the birth of the internet, the cloud servers, so that the computing could be amortized across multiple tools and multiple designers. So all this is very good, but the problem is that where we stand today, each of these three key elements is being disrupted in a significant way. Let's start with the PPA scaling. We're now finding, if we look back over the past couple of technology nodes and the coming nodes in the next few years, what we see is that the scaling gain that we get in the improvement in the reduction in power, improvement in performance, and reduction in area, the percentage gain is shrinking. It is almost a half of what it used to be and is going to get even less, which means the pressure on PPA improvements is going to increase. The second is that the only way we got the Moore's law scaling till now is by more complex fab process, which also means that the number of corners at which the designs have to be closed or converge has exploded. And that's getting beyond the capacity of the combinatorial optimization algorithms that we have, and is causing another problem for us. And finally, precisely because of that problem, we also now have to run the tools through many more iterations than we used to, which also means that the computing expense is almost going up 10x. So you look at these three different disruptions that are affecting us, and it's clear that the current design methodologies and processes are not going to be viable looking into the future. So we have to have something new that is going to help us deal with this disruption. So let's look at the challenge from a design perspective. So we talked about the scaling problem in PPA, and this is a conceptual graph that gives you a rough idea of, if we look back over the past 3 or 4 process nodes and look ahead as to how the gains, and this is the percentage gain, not the absolute gain, is reducing for all three: power, performance, and area. And this is already causing a serious challenge for our designers, because the only way to make up that shrinking gain is to do a better job of the design. And that's what we're calling the design advantage curve. So we have to have a design advantage on the PPA to compensate for the decreasing advantage we're getting from the let me try to get rid of this. No, I can't. That we're getting from the PPA. And the accompanying problem is that we have to provide this design advantage with the designers while still keeping our development cost constant. And I want to elaborate on this point in the next slide. So if you take a holistic view of this problem, then what we see is that there are really four parts to the problem. The first is that we are, of course, trying to reduce the cost of the chip and the product generation over generation. And this means reducing chip area, which of course the place and route tools address. But we have to do this while also keeping the yield at a good number. And as we said, because of more complex fab, this means that we have to close designs at multiple corners. We also have to pay attention to the test time, which means in terms of the scan insertion, we have to make sure we're doing a better and better job of minimizing the test time. And finally, we have to take into account the packaging and the coming disruption in terms of 3D ICs to make up for the fact that Moore's law is at scaling. Now, all of this has to be done while keeping the design efficiency, which directly impacts our operating expense. So it doesn't help us a lot to have tools that reduce the cost of the product if they're going to increase our operating expense. And that is where the current problem is. The number of synthesis iterations, DV iterations, place and route iterations are all exploding as we go from one generation to the next, which also means the license cost is going up. So both in terms of the non-recurring engineering and the license cost, the operating expense is significantly increasing, and that's not a viable situation going into the future. Coupled with that, obviously, is the capital expense, because running the tools more often, more licenses, obviously means we need more compute cost, also means that we have more emulation cost, all of which is very good for the FPGA and compute and EDA vendors, but not so good for the chip vendors. And finally, all of this has to be done while also optimizing the power and performance, as we said, to make up for the shrinking gains from the technology. So any research that we do into CAD, design automation tools going to the future really has to address this holistic picture. It doesn't help a whole lot to have algorithms that will shrink the chip area if the operating expense is going through the roof, or the capital expense is going through the roof, or you're not really getting a power performance gain. So it's really critical that, and this is what we do at Qualcomm, is to really look at this big picture and develop techniques that really address all aspects. So to address this problem, let's step back and look at where is the design effort going and why is the design effort getting more complicated. So this is a very typical design loop that the designers go into, whether they're doing the front-end synthesis, design verification, or physical design. In all cases, the designer starts with some design and then chooses some design parameters to optimize the PPA, or if you're doing design verification, they'll choose some constraints to drive the test vectors. Then we go into the traditional EDA tools, whether it's place and route, timing analysis, power analysis, or coverage analysis. And we'll run the tools to find out what quality the design has, what we call the quality of result metric, which is in fact the PPA, and then some other metrics. And the designer will look at those metrics and decide how should he tweak the design on the next iteration to try and get the PPA to meet the targets that have been set for the product. And this loop goes on. And the bottleneck is that as the challenge on PPA optimization increases because of shrinking process gain, the number of iterations we're going through is increasing. And there's also a long turnaround time, because as the designs are more complex, the tools take a lot longer to do the place and route, to do the timing analysis, to do the power analysis. And so you get a double whammy, because you're spending, each iteration is taking longer and you're doing more iterations. So let's think about how can we address this problem. So a lot of work has been published on trying to draw the analogy between this design iteration loop and reinforcement learning. And of course, these are largely people who are coming from a pure AI perspective as opposed to a chip design perspective. Now, in the AI perspective, this design loop can be made to look like a reinforcement loop where you think of the designer as a machine learning agent or reinforcement learning agent. You think of the selection of the design parameters as the action. You think of the evaluation of the impact of those actions as the tools that will tell you what the PPA is with those parameters. And then you measure some reward, which will be the QR coming out of that. And you also look at the state, which in this case would be the design change or the design revision. And you try to update the agent to say, well, what parameters are going to optimize my reward function? Now, like most analogies, it looks good on paper, but it breaks down very quickly. The first thing is that in contrast to things like AlphaGo and chess and other games where this has been applied, chip design is not just a game because it doesn't work according to structured rules like the rules that you have to move a piece on a chessboard, but it's a creative process. And the designers actually will take actions that may not even be in the rule book, but they know that this will actually improve the PPA of the design. And there is no way to capture that in reinforcement learning training. But even if we set that aside, the other two big problems we face are that the reward function in the reinforcement learning paradigm, because it wasn't designed to be a constraint optimization paradigm, has no way to capture the design constraints other than to try and create a weighted reward function where you assign some weight to the different things you're trying to constrain and optimize in the hope that you can constrain some and then optimize the others. But you really can't, for example, put a hard constraint and say, give me the best power and performance within a fixed area. So that's a fundamental problem with reinforcement learning. The second problem, which is an absolute showstopper, is that in this loop, the evaluation with EDA tools can take for each iteration in the training process at least a day, if not several days or even a week. And reinforcement learning algorithms are still at the point where you need tens of thousands of iterations to really train anything. Now, how people are trying to get around that is by approximating the output of the tool without actually running the tool, by having some approximation function that approximates the reward for the given design parameters. And as we will show, that is actually the crux of the problem with the EDA tools today, that there is a large gap between these approximations and the actual QR that you get when you've done the real design tool. So to really find the right solution to the problem, let's look at what really is good about the current algorithm-driven CAD and what actually is the weakness. And then we know what should we actually address. So when it comes to the automation, clearly the synthesis, the DV simulation, the place and route tools have proved that they can in fact automate fairly complex designs with millions of standard cells. And that really isn't the showstopper. But the iterative optimization we just talked about, which takes several days or weeks to meet the PPA, that is the problem. And in some cases, even after all those iterations, the design doesn't converge and the designers have to go in and do manual adjustment. So this growing gap between the capability of the automation and the target PPA that can be achieved is the source of the problem. This leads to the resource problem, which is that within the tape out schedule, I have a limited number of iterations I can go through. Now, the only thing I could do to increase the iterations is I could have more runs of the tool in parallel with more licenses and more compute. But as we said, that doesn't scale because now you're just having your operating expense go through the roof. On the converse side, because you can't indefinitely increase the number of iterations, you tape out with a suboptimal PPA, which means your chip is not competitive. So we have to find a way to cut the iterations. There is really no other way out of this problem. And the root cause of these iterations, if you stop and think about it, is the fact that the estimates that the tools make, that the optimization algorithms make, differ largely from that achieved. Because all these optimization tools, when they go through the optimization process, they start out with some estimate of what they think the QR will be, and accordingly they adjust the design, and then they run through the actual place and route or synthesis and find out what really came out the other end. And of course, there is a gap. And the problem is that as we get into deep submicron, this gap is growing. It is already quite bad, and it's getting worse. So there has to be a better way to do this. And we need fast and more accurate QR estimation, which is a challenge. So not only are the current estimations inaccurate, but if we want to get an accurate one, we have to run the entire tool, which makes it very slow. And then there's another layer on the problem that apart from the estimates within the tool of place and route and synthesis, for example, there is also the problem that synthesis needs to look ahead to the impact of its decisions on physical design. Physical design has to look ahead to the impact of decisions based on the process corners, for example. So there are many, many loops in this iterative process, all of which rest on one fundamental thing, and that is, can I predict with a reasonable accuracy and very quickly what the quality of the result is going to be? So can data-driven CAD help? That's the next question we ask. And if we stop and think about it, how does the designer do this? When the designer is iterating, he builds up an intuitive map in his head of how the design parameters are impacting the QOR. And it's that intuition that drives him to figure out, or her to figure out, how to pick the parameters on the next iteration. So it's really a mapping of how the design choices, the design parameters are impacting the PPA, is the mapping that the human designer is intuitively building up. And that's exactly what supervised learning is designed for. It's designed to learn the cause and effect. In this case, the cause and effect between the choice of parameters and the QOR. And if there is some systematic relationship between these two, no matter how complex, supervised learning can be trained to learn that, provided you have the data. And the nice thing about this is that if you can do a model based on supervised learning to predict your QOR with a high accuracy, it will also scale. That means that even as your designs get more complex, whether it's a 10,000 standard cell or 2 million or 3 million, the model will scale because it effectively is learning a functional mapping of the features, which is independent of the size of the design in this case. Thirdly, the estimation will run a lot faster than running the EDA tool itself, because of course we now have a mathematical function that is approximating what the tool would do, and we don't have to go through the actual task of doing the synthesis or place and route to get that estimate. And that's because when we're in the optimization process, we don't actually require the entire solution of the EDA tool. We need a good enough approximation to what the outcome would be to decide how can we optimize. So this thinking is what leads us to believe that supervised learning could be a very good tool for QR estimation, which in fact is the root cause of why we're doing so many design iterations. So if we get a good estimation, we can potentially cut down the design iterations and solve the problem that we're stuck with. So in supervised learning, what is the challenge to do QR estimation? Supervised learning at a very simple level essentially allows you to train a mathematical function, y, that is a function of some variables x, provided you have some x and y known data to train on. Now, the challenge in implementing this is the following. First, you have to formulate the problem as a machine learning problem, which at a very high level, you can say that y is the QOR and f is the design parameters. But that's a mouthful, because how you represent these design parameters, and Brusek talked about this a little bit yesterday in the talk from NVIDIA, is critical in deciding whether the model can actually learn and the features can actually be extracted from the design that are critical to the learning process. And that brings us to the data representation, which is how do we actually represent the design data? And the in our case, in contrast to speech and face recognition, which have been extensively researched by the AI community, we deal with net lists, not faces of people. We deal with placements, not speech coming out of people's voices. And these are very different kinds of data. And the representations that have been highly developed in deep learning for image and speech do not map to these at all. And one of the representations which is very critical here is, which Brusek talked about yesterday, which was developed by Professor Max Welling at Qualcomm, is graph neural networks, which turn out to be the most natural representation for netlists, for example, and allow us to extract the features that we need to learn from for the design. Then we have to figure out a good enough set of designs to learn from so that the model will generalize. We have to figure out the KPIs that um, the performance indicators that we care about for the PPA that will be impacted by the model, because any machine learning model will have some inaccuracy. And remember, that's the problem we're trying to solve. We're trying to get a more accurate QR estimation, right? And so based on this training, we can get that, but how accurate the model is depends on how we design this so-called loss function. And how we design the loss function, which determines the accuracy, has to be closely coupled to the impact of the inaccuracies in the model to the final impact in PPA. So for example, suppose this model is being trained to predict the timing, which is the performance in PPA. Now, an inaccuracy in that prediction could cause the design tool to make a choice that might increase the leakage power by adding more buffers than it should, right? So you want to have a direct linkage between the impact of the inaccuracy of what you're trying to predict with the model to the final impact on the PPA of the design. And by reverse engineering that, you can get a good loss function and an accuracy target that will actually make the QR accurate enough for the optimization purposes. The next problem we have to deal with is the fact that the training data we have is very limited. It's easy to get millions of photographs or speech signals to train deep learning on image and speech, but none of us have millions of designs lying around, because most companies, we tape out, maybe a dozen or 2 dozen chips a year, and that's about all you have to learn from. So how do you learn from very limited sets of chips? And that's a paper we published in NeurIPS last year, where when you're looking at the graphs for a netlist, for example, or graphs for anything, how can you actually learn from a very limited set of graphs? And that's the kind of work that we also do internally. And so all of these factors that play into what I would call the framework for the supervised learning problem is something that we have to develop in this community, because the AI community has, of course, developed very refined problem formulation, data representation, loss functions, all of which are geared at face recognition and speech recognition. None of them are useful in our domain. And that's a point that Bruce made yesterday, which I thank him for. And I think in this community, if we want to advance the state of the art, both from a machine learning point of view and CAD, this is something we need to focus on, which is how to improve and get better data representations, how to deal with very limited data, how to get our loss function designed so it truly relates to the final KPIs that we care about. So assuming that we could solve that problem, then we could use such a supervised learning model to do the QR prediction more or less as a proxy for the EDA tool that the designer would have run to find out the QR. And if we did our job right, then this model will be very accurate, and accurate enough that it'll be close to the actual QR metric you would have gotten from the synthesis or place and route tool, or if it's a coverage model from the design verification tools. And it would save the designer time in 2 ways. One is because the model will predict the QR faster, and in our experience, by the way, that's a 10x improvement. Bruce shared an example yesterday on power, on switching activity for power, which also showed a 10x. But I would say across the board for PPA, we find that the supervised learning models give you about a 10x improvement over running the EDA tool. But there's another benefit. Once you have a mathematical model to actually predict the QR, the designer can use that model to do a sensitivity analysis, and therefore perhaps do a better choice of the design parameters with less iterations. And we'll demonstrate some results of that in the coming slides. So from a mathematical point of view, what we're really doing here in QR estimation is we're using supervised learning to do nonlinear interpolation. But the nonlinear interpolation with machine learning is quite different than what some of us may be used to coming from classical math background, in the sense that we're not trying to take, n points that we know on a curve and then interpolate the other points on that curve by doing some kind of curve fitting. And that won't really help us, by the way, because then that curve would only work for the design we trained on and may not generalize. So in machine learning, what we try to do is that if the design is characterized, let's say with the EDA tools at some small set of points, let's call that M, then we interpolate the QOR at the remaining points by actually learning what are the features of the design and the parameters that are impacting the outcome of the QOR. And in many areas of AI, this kind of interpolation problem has been studied and solved. And in our case, it really boils down to interpolating a multidimensional function where X, Y, Z could be the design parameters or the PVT parameters. And of course, you could have more than 3. And you're trying to figure out the QOR, which could be the W. So now I run the actual tools to give you the value of the W at some subset U of the design points. And now I say for all the remaining points in the design space, which are uppercase W, I want to find a function that will calculate that based on what I already knew about U. And remarkably, you can do this very well. And I've taken the liberty here to lean on some of the results from NCSU, from Paul Franzen and Rhett Davis. We have similar results internally, but I thought this would be more useful because our results obviously are not in the public domain. And for those of you who want to really follow up on this line of thinking, you could benefit from a lot of the data that NCSU has gathered for their research. So what we're showing here is the QR prediction for a place and route tool, where these are the input parameters that the designer can play with, and these are the output PPA metrics that you would measure at the end of a PNR run. And the question is, can I find a supervised learning model that would map these input parameters into these outputs for any given value of the input parameters and for any given design? And this is kind of a result for a Cortex SoC, which builds such a model through where it takes 50 runs. That means that we have 50 data points, and from those 50 data points, the supervised learning model will interpolate a function that will tell you the output values, in this case, the performance the whole time, but they've done this model to do all the parameters for power and performance. So it can tell you the performance, and here we're showing it as a function of 2 parameters just for representation, but of course, they've done this in hyperspace for all the different parameters that the designer might tweak in the physical design. And this is really quite remarkable, because once you have this kind of representation, then you can not only very quickly get feedback on saying, well, if I picked this parameter value here and this parameter value here, what would the whole time be? But I can also use this function now to get insight to say, well, how should I change the parameters to reduce or increase my hold time as the requirement might be? And they had a student project where they had a number of students do the design completely manually without using the PNR tool, without the benefit of the model, and then also do it with the benefit of the model. And what the net result that came out of that was that because of the insight the model produced to get to the final PPA target here, took 4 iterations with the QR model, whereas with the traditional QR place and route tools, which of course use their own estimates, it took 20 iterations. So not only can we cut down the time for iteration, but we also cut down the number of iterations. And I would say that, in all the research we have seen globally, this work comes closest to what we also internally observe and think is the way to go at Qualcomm. Now, the question is, can we attack this other problem, which is if we have a good tool to predict the QOR, can we help the designer further in figuring out how to select the optimal parameters using that model? And I'd like to share some results here from Rhett's work also, and which is again a student project. And by the way, that's one of the remarkable things I find in this research direction is that the students who are effectively a proxy for designers and are all individuals will all come at the problem in a different way. So in one shot, you get 50 or 60 ways to do the design, and you can learn from that. And again, if you use the power of machine learning, that can certainly generalize to how some other designer might have done it. So in this experiment, what they did was to use the models to predict the outcome, and then have several designers do the design with different technology targets, right? Where we have different layers of metal, and as you would expect, as you increase the level layers of metal, you can get to a faster timing and also a lower area. And these plots are essentially picking the best design and labeling that as the optimum. So the question is, could we actually, with machine learning, have arrived at those optimum designs without human intervention? And I'll show you some very interesting results from Rhett and Paul's work there. But there's an even more interesting question in this plot that I want to draw your attention to. If you look down here in the bottom left, there are these curious looking black circles, which actually you can see give you an even more optimal design than designs we have on these plots here. These are designs which reflect the creativity of students who decided to not just use the automated EDA tools with the QR prediction models, but actually get creative about fiddling with the design itself to improve the area and performance. And this is the point I was making earlier about reinforcement learning, that this kind of creativity, which the human designer comes up with, we still don't really have a paradigm to capture that. And that's something that's worth doing research into. And some of the work here that exploratory work that the students did with in Rhett and Paul's group was to look at genetic algorithms to which would be a natural fit for this kind of problem, to see as it goes through the iterations with these surrogate models to evaluate the QOR, can it kind of learn what the human designer is learning as an evolutionary process, and pick better and better parameters to improve the PPA. And what you see here is that it does succeed in doing a pretty good job on reducing power and area, and there's more room to go to sort of get all three vectors, all the PPA improved. But we feel that this is a very promising direction, because genetic algorithms, in contrast to reinforcement learning, have one property from a learning perspective, and that is when the search space gets very large, which is our problem, then they're far more efficient in the learning process. And we did a simple math, for example, of our chips. If we were to just look at, for example, place and route and floor planning, right? What is the combinatorics given the number of macros, number of memories, number of subsystems, number of routing channels? If you put it all together and we look at all the combinatorics of how this could have placed and routed, the number comes out to 10 to the power 15,000, just to give you an idea, right? And when you have that kind of larger space, you're far more likely to be successful with the learning algorithm like genetic learning than other kinds of learning techniques. So so with these observations, we return back to our question of whether algorithm driven or data driven CAD, whether these are really in competition with each other or they can complement each other. And so if we take away this key observation of how the data-driven CAD can help us with QOR, it leaves us with the following observation, that the algorithmic CAD, which is based on analytic solutions, it does need human guidance. And as we've seen, that is the bottleneck and the problem. But the advantage of the algorithmic CAD is it does do a very good job of the automation. And of course, it produces the accuracy that we need for sign-off. The data-driven CAD, through the QR evaluation models, and possibly the evolutionary algorithms like genetic algorithms, can guide the algorithmic CAD to optimize the PPA much faster than we're currently being able to do with countless iterations of the EDA tools. So in that sense, the data-driven CAD gives us a paradigm for very fast and very cheap in terms of the compute expense. Remember, we want to keep our OpEx down, less licenses and less compute. And it's accurate enough. And I think that's what the research at NCSU has shown. That's what our own research shows, that these are accurate enough for the optimization process so that you can, in the initial phases of the design, lean on that before you go to the EDA for the sign-off. And so that really says that these are not competitors, but they really are collaborators. And where we want to head into the future is to continue leveraging the incredible automation that the EDA industry has given us, but complement that with this emerging technology of data-driven CAD that could give us the PPA optimization within the resources, within the OpEx, within the time frame that we need, especially to compensate for the shrinking PPA gain from the fab process. So with that conclusion, we come back to our cliff and make the observation that one way, I would not claim it's the only way, but one way that we can manage this disruption and keep our foundation from crumbling is to leverage AI to manage this disruption. And in that sense, I think MLCAD will almost become another building block in this foundation, along with fabless chips, design automation, computing. MLCAD will, in the coming years, become the fourth brick in this foundation to make sure that the rest of it does not crumble. And to summarize, what is the leverage we're getting from machine learning? The first is the ability of supervised learning to learn from design data that we already have. And this is critical because now that design data is capturing some of the human intuition that we actually want to learn from. And we use the nonlinear modeling capability of or interpolation of supervised learning to learn from that design data and then be able to interpolate that learning to other designs that it wasn't trained on and larger designs than what it was trained on. And finally, the learning that we can get from algorithms like genetic algorithms, which can continuously optimize because every time you run them, they learn a little bit more and can further improve the design. So instead of having to do 10,000 iterations or 20,000 to train the tool and then benefit with something like genetic algorithm, you can start benefiting very early on in the iterative process. And the more you iterate, the better it gets. So I think these are three very key points of leverage that we can get. And in conclusion, the last thing I would like to say is that to make this vision a reality, which is how do we combine the data-driven CAD and estimation tools with the algorithm-driven CAD, we're obviously going to have to evolve an infrastructure for that. Because right now, these two technologies are living in very different worlds. And fortunately, the SI2 org has created this year a special interest group called the AI ML group, where several companies and universities are already participating. And if you share this vision and want to help bring this to life in the coming years, this would be a great forum to get engaged with, to contribute your ideas as to how can we accelerate not only the development of the machine learning data-driven CAD, but also the integration of that with the traditional EDA. Thank you very much for your attention.
All right. Thank you very much, Rajeev. Thanks, Punjab. Are there any questions, please? I've got both the chat line and the... Okay. So you touched on this right at the end, but you know, even within a company, how are you going to collect all this information across your 10 tape outs a year, which have thousands of modules in them, which have hundreds of thousands of compute hours behind them, and organize that in a way so that, first of all, you have the data-driven models that you need, but secondly, you know when you're out of the bounds of the models that you've built, because then you can be easily misled. And I'm curious how you think about handling that as a company.
So I'll have Pankaj address the first question, which is a very critical question because, as the euphemism goes, data is the new oil. And Pankaj, do you want to address the first part of the question, which is how do we address the fundamental issue of collecting the data?
Yeah, it's a very good question. It's a tricky question in some ways. I mean, you would imagine that we would have access to not just current SOCs, but all the past SOCs that we have done. But that is not very easy. to do. And we are actually evaluating some tools right now to look at IP retention and collation. So it is not just, oh, I have all the tape-out databases and netlist and RTL and all of that stuff, but you have to categorize them, you have to label them and be able to feed them into the ML tools. So we are in the process of doing it. We definitely don't have an ideal solution yet.
Okay, and Paul, I forgot, there was a second part to your question. Could you
The
remind
second
me?
part of my question is, past designs had their own constraints and their own design parameters. You could easily be designing in a space where you're being misled by your past data. And how do you avoid that?
Well, that's a good question, Paul. And you and Rhett are obviously researching, and that's actually the cornerstone of the research in this area. And that's where the machine learning intelligence comes into the research that we're doing, which is being able to recognize what you call as misled, right? Which is being able to recognize the deficiencies in the data we're training on, being able to design experiments that would expose whether the representations, we talked about the graph neural network, and the features that we derive from those representations are adequate or not. And so we have to design experiments that would show us whether the model is scaling, whether it's generalizing, as you said, across different types of modules, because the topological structure from a connectivity standpoint, if a block in a CPU might look very different than that in an audio processor, for example. And then we have to generalize across technology nodes. But when you stop and think about it, there are underlying features of the design, features of the process technology, right? That their values will change over time with the designs and the chips, right? But what those features are that are actually influencing the outcome, many of them actually remain stable. There may be an additional feature that a new process might bring in, or an additional feature that a new block on your chip might bring in. But a substantial number of the features that you learned will still be the same. So the crux of the problem is, how do you zoom in on those? And that requires, as I said, that's where the machine learning intelligence comes in, is all the methods and techniques to prove out that you actually have discovered the right set of features through your representation. And also, the one thing I skipped over in my supervised learning slide is you have to design the validation criteria. So remember, I talked about the relationship of the end KPI with the loss function. There is also the validation experiments that you have to design to expose the kind of things you're talking about, which is, in my validation, am I including a design problem that is sufficiently different than what I trained on, right? And would trap anything in my training that would mislead me. So these two aspects of the designing the validation experiments, and that's really what I meant by design experiments, that's really critical to this process as well. But the short answer to your question is, having tried to do that over the past few years at Qualcomm, we have learned that you can actually do it.
Okay.
That's the only hope I can give you. I'm not going to tell you how.
Okay, good. Thank you. Any other questions, please?
Yes. So first, thanks a lot, Rajeev, for a great talk.
Thank you.
It's impressive because I feel that most of the talks here relates to the physical design or in Q&R area, and I come from the verification area, and we kind of it was very much aligned to the conclusion that I got with my own journey in this area, and it's put things in a very clear and inspiring way. So
thank you.
Many thanks. Now, I think
well, and I have Pankaj to thank for. So he keeps me grounded in reality.
Sure. So I think that there are a couple of terminologies that comes out, some from active learning, when we have when we choose the next point that we want to evaluate, because evaluating a point is costly.
Yeah.
But here it's quite unique because we have the entire space that we can choose from, It's not that someone already, but what we need to choose is which points, not just to estimate, but to simulate,
Yes.
right?
Yes.
And the other thing that we are very biased, that we don't want to learn the entire space. We are focusing on one, we are aligned with the optimization process we are trying to do. So
Yeah.
in this sense, you know, as you showed, learning from 50 points, I can hardly believe that it is accurate on the entire space, but it should give information about the areas of these points, because it cannot learn of the areas that, as you shown, as the creativity areas that were not given to the model to learn from. So we are back in the exploration exploitation game, and here what your supervised learning and is giving is the exploitation part, and the creativity is the exploration.
Correct.
And you need to find the balance between them, and the genetic algorithm is one way to try to get to a creative areas, and you know, adding some randomization to the process is another way. So what are your thoughts about, you know when you so for me the point that you of the creativity falls pretty nice into the exploration part of the reinforcement learning framework. How do you see it?
Yeah. So like I said, I mean, there's a piece that is purely creative, like I said, which is I think we're still a long ways from figuring out how machine learning is going to do that. But if we separate out the two parts of the creative, what we're calling creative, one is where the designer is not necessarily introducing some new option in the design process or in the design itself, but is sticking with whatever options are given to him, but just making an intelligent choice of the options, right? So that part, as Rhett's research shows, the genetic algorithms are able to learn and explore. That's the exploration part, as you said. That part of the creative exploration, they can learn very well. But now when we get to the second part, which is they're going to go beyond the options you gave them, right? And invent a new option that didn't exist. I think that's the next frontier beyond all the stuff I presented today. But if we can give the designer today tools to even automate the first two things we talked about, which is the QR estimation and the exploration of how do I pick from the available options the best, right? If we can even do a better job of automating that through supervised learning and genetic algorithm types of learning, then we at least free up the designer to have more time to do that creative solution where he creates the new options, right? And at the end of the day, that's what we're trying to do. We're trying to get the best PPA within limited time. So I'm thinking of a direct answer to your question, but that's my view on it.
Yeah, thank you.
Sure.
So does anyone else have any questions? I was about to ask one. Yeah, thanks, Will.
If I may, Rajeev and Pankaj, that's very, very impressive talk, really very insightful.
Thank you.
I have maybe a little bit philosophical question going through my mind, which is that when you were talking about your surrogate models, Rajeev, and the success with them, so we've been building models in design for quite some time. So for example, in analog optimization, there are some people who run SPICE simulations all the time, so they are very accurate. And there are other people who build response surface models using regression techniques. This is much, much faster evaluation, but you may not get just as good a result. So it's the old trade-off, accuracy versus time. So what is it? What is the, do you have an idea? What is the fundamental underlying breakthrough that machine learning based models appear to be much more powerful than more traditional, let's say, regression based models?
Yes. So I tried to allude to it, Ulf, in passing, and your question gives me a chance to elaborate. So consider the following. Suppose that you're trying to, let me take an example. So suppose you're trying to predict the power that you're going to get for the certain circuit, right? And like you said, you could simulate this thing. Now, the power, and we know from the physics, depends on the components in this circuit, right? The problem is that the circuit is too complex. We can't write down all the physics equations and calculate them, or that takes too much time. And by the way, that's what EdgeSpice does. EdgeSpice will actually walk through all the physics equations and simulate them, right? Now, consider the following, that in a classical regression or interpolation or extrapolation, what I would do is I would find a few points from EdgeSpice of the performance, and then I'd try to find some kind of mathematical function that would fit these points and extend to other points I didn't simulate.
Yeah.
Machine learning does something different, and that's really key to understand. What machine learning does is it says the behavior in EdgeSpice for these different choices of component values that you picked, right? There is a certain relationship between the component values and the behavior, right? Now, suppose I change the circuit, right? At a component level, that isn't going to change. So the capacitor will still be a capacitor, the inductor is still a inductor. What I really need to learn is, if I recompose this circuit with the same elements, right?
Yeah.
I now design a different circuit. Can I predict what that circuit will do in EdgeSpice? Which is really the ultimate extrapolation you want to do, right?
Okay.
Now, if you could correlate two things, you could say, what are the features of the composition of any circuit, right? I take that into my machine learning. So I have some features of the composition. I know the underlying relationship between the component behavior and the circuit behavior, right? If the capacitor has value C, I'm going to get impedance 1 over J omega C, whatever, right? I know that. So if you combine these two things, you get a very powerful modeling and interpolation technique, which is not simply trying to fit the points on the EdgeSpice that you already measured. It's trying to understand, why did EdgeSpice produce this result for this circuit, given its composition and given its components? Can I extend that to any arbitrary composition and any arbitrary circuit? And you can actually do that. And that is effectively what Paul and Ritz, the little example they showed on the Cortex SoC, that's effectively what it is showing. That there are some features that they are learning of that design, right, which allow them to get this nice model, you know, which works from 50 points, it extends to almost anything. Because you're right, if they took those 50 points and then tried to fit some nonlinear math function, there's no way they were going to get that beautiful three-dimensional curve.
Yeah. Okay.
Rajeev, if I may add.
Things, yeah.
Please, Pankaj.
Yeah, if I may add to that. So Rajeev gave a very good example of Spice, you know, as design changes and evolves, how do you use ML? But I want to give another example of maybe static timing analysis. And we have lots and lots of corners because you're trying to optimize for power performance and the process nodes are getting complicated. So there could potentially be hundreds of corners that you want to sign off on. And if I understood your question correctly, how do you balance the ML with the sign-off quality that is needed? So at least our thought process internally is as follows. Yes, you still have to sign off at the greatest possible accuracy. But a lot of design work is happening in this iterative optimization loop that we talked about, where you don't need to analyze every design element at all the design corners, right? ML can predict which corners are dominant, which corners generally tend to impact the final sign-off the most, and they can be predictive. So it allows us to, if you think of design as a funnel that is iterating and kind of converging, it allows us to get there faster without spending a lot of time, money, compute, license costs, etc.
Yeah. Thanks.
Thank you very much. Well, that brings us to the end of the hour. Join me in thanking Rajeev and Pang Tang PanCAD for excellent talk. Silent
Thank you.
clap.
Thank you very much for having us.
At this point,
Bye.
I'll hand it off to Bei Yu. Thank you very much, Bei.
Okay.